Hello, welcome to this lecture of this course Computer Aided Power System Analysis. In the last class, we have discussed about the two methods of the AC/DC load flow. The first one we discussed about is the simultaneous method of AC/DC load flow, and the second one was the sequential method of AC/DC load flow. And we have seen that in the case of sequential method of AC/DC load flow, there is no change in the Jacobian matrix, there is no change in the number of unknown variables, there is no change in the number of mismatch quantities. So, then therefore, there is a very little amount of change which is to be done in the code of the power flow solution as compared to the case when we are trying to solve this AC/DC load flow by utilizing the simultaneous method. In the case of simultaneous method, we have seen that the Jacobian matrix involves 5 more Jacobian submatrices. Also, the number of unknowns increase and also the number of mismatch quantities increase. So, then as a result, the overall size of the Jacobian matrix increases. So, as a result, the computation burden increases quite significantly in the case of simultaneous AC/DC load flow. On the other hand, in the case of sequential AC/DC load flow, because there is no change in the size of the Jacobian matrix, so then therefore, the enhancement in the computation time as well as the computation complexity is quite minimal in the case of sequential load flow. So, as a result, you would be pursuing the sequential load flow. Let us look at the schematic diagram of so we have got this is the AC terminal bus, then from this AC terminal bus there is one transformer, from this transformer then this is the converter terminal bus, then from this converter then we have got this is the converter and then this DC side. So, we call it as V terminal angle theta terminal. This transformer has got a ratio 1:a. So, this has got a tap changing transformer. This is I prime, sorry, this is I primary, this is I secondary. This is the converter terminal voltage E s theta s. This is the DC current, this and this is the DC voltage. Please note that in the case of an HVDC link, this arrangement is present at both the ends. That is, if this is the rectifier side, for example, if you are saying that this is the rectifier side, identically the same arrangement is also present in the inverter side. So, then therefore, if we discuss in detail about one particular terminal, so then automatically that discussion extends to the other terminal. So, now what happens, as we have said that in the case of AC/DC load flow, we said that we have got some quantities which are unknown quantities, and we said that these unknown quantities are given by this set or by the vector x DC. So, now we have to first understand that what are those unknown quantities, and then subsequently we have to understand that what are the equations available to solve these unknown quantities. Now, what happens that for now here in this course we are talking about, as we have already said, that LCC HVDC only. So, line commutated converter based HVDC, this is nothing but this thyristor based HVDC, thyristor based HVDC. Now, in the case of any terminal, I have got different unknown quantities. For example, now for any rectifier terminal, there is something called quantity alpha, which is called the firing angle. This should be apparent for anybody who has done the basic course on HVDC transmission. Similarly, for the inverter terminal, there is a quantity called gamma, which is called extinction angle. And we also define something called power factor. At both rectifier and inverter. This is not defined, this quantity is not defined, this quantity is not defined. So, this also we take unknown as unknown. Now, here if we look at this, so then what are the things we can say that which are unknown? Here this Vt theta t are nothing but the AC terminal voltage. So, then therefore, this Vt and theta t would be solved by the AC load flow codes. So, then therefore, as far as the DC system is concerned, Vt and theta t need not be included as their unknown quantity, because this Vt and theta t would be solved as part of the AC load flow code. And here we are left with Ip, Is, A, Es, theta s, Vd, Id. Now, here there are many quantities. Now, the question is, out of these quantities, which one should we take as an unknown quantities and which one we should actually leave out. Now, to understand that, first let us look at the equations for any HVDC terminal. So, let us look at the equations of the, we have to understand that what should be our unknown quantities, but to understand that, first let us look that what are the equations available to us, and then by looking at these equations it would be relatively easy for us to identify what should be our unknown quantity. So, equations for the HVDC link. Now, we will write three parts of the HVDC links. Now, there are actually three parts, one is rectifier, one is inverter, and one is DC link. One is DC link. So, now the equations corresponding to rectifier are VDR. VDR is nothing but the DC voltage at the rectifier side. For example, here in this diagram, if this is a rectifier, so then this Vd is nothing but VDR. So, then VDR, it is given by 3 root 2 by pi NR AR ETR cos phi r. It is called VDOR cos phi r. Now, what are these quantities? ETR is nothing but the terminal voltage. For example, in this diagram, here we have actually denoted this terminal voltage to be Vt, but in this equation this ETR is nothing but the terminal voltage at the rectifier side. AR is nothing but the tap changing ratio at the rectifier side. For example, here this transformer has got a tap changing ratio of 1:A. So, then corresponding to rectifier, this is AR. Phi r is nothing but the power factor angle. Phi r is nothing but the power factor angle. NR is nothing but the number of converters at the rectifier side. Now, what happens that to understand this, just let us simply recollect that for an LCC HVDC, usually it is 12 pulse HVDC always. Now, because it is a 12 pulse HVDC, so then what happens that at the DC side we always connect two 6 pulse converters in series. So, two 6 pulse converters in series, they are connected in series at the DC side. So, this is the total VDR and this is ID, and at this side one is, so at this side, so this is basically AC voltage. So, this is AC voltage, AC grid. So, this is AC grid, and then from this AC grid there are two converters which are fed by two separate transformers, and these two converters are connected in series. As we know very well, I mean whoever has gone this very basic course in HVDC, one of the transformers will be connected in star star, another one will be connected in star delta. This is just to eliminate the harmonics, etc., etc., but I mean these are actually beyond the scope of this particular course. So, we are not going into this detail of this. Now, here what happens that when we say NR, NR is nothing but the number of 6 pulse converters used in an HVDC terminal. Now, for a 12 pulse converter, we are using two 6 pulse converters in series. So, then therefore, for 12 pulse converter, NR is equal to 2. So, NR is equal to 2 for 12 pulse converter, right. And then the another equation is also VDR is equal to VDOR cos alpha. This alpha we have just now said that this alpha is nothing but the firing angle, minus 3 by pi XCR NR into ID. XCR is nothing but the transformer leakage reactance at the rectifier side. This is the individual transformer reactance. Please note that this is the transformer reactance of one transformer. For example, here we are using two transformers. So, then this XCR denotes the leakage impedance of one transformer. It is assumed that this leakage impedance of both these transformers are identically same and etc., etc. So, when we do this calculation, we always assume this case that basically these two transformers are identical in nature. So, then therefore, their XCR are all same. In case they are different, so then in that case this analysis becomes too complicated, but usually whenever any HVDC link is put into practice, it is always endeavored that these two transformers are identical in nature. So, then therefore, there is not much of an error to assume that this XCR is same for all for actually both these transformers. So, XCR denotes this the transformer leakage impedance of one transformer. Similarly, at the inverter side, same equations prevail. So, VDI would be given by 3 root 2 by pi Ni. Ni is the number of converters, or rather number of 6 pulse converters at the inverter side, into AI. AI is nothing but the transformer tap ratio at the inverter side, ETI cos phi I, that is given by VDOI cos phi I. Now, here we must for the case, so this quantity is actually VDOI, we denoting is that this is VDOI, and here we are denoting that this quantity is actually VDOR. So, VDOR cos phi r. Phi I is nothing but the power factor angle at the inverter side. So, another equation at the identically same type of equation, VDOI cos gamma. So, this please note this difference. In the case of rectifier this is alpha, but for the case of inverter this is gamma. minus 3 by pi xci n I I d. Please note that this we are not writing IDR and IDI, because you see for an HVDC link the current at the rectifier side and the inverter side, they are same. So, then therefore, ID is same. So, then therefore, we are not at all differentiating between the currents at the rectifier side and the inverter side. So, then we have got 4 equations 1, 2, 3, 4. I suppose I should write down all these quantities whichever we have not. So, we write that Nr or Ni is the number of 6 pulse converters connected in series at rectifier or inverter site. Then AR or AI is transformer tap ratio at rectifier in bracket inverter. And then we have ETR, ETI, then we have ETR or ETI, that is at AC terminal voltage at rectifier inverter. And then we have XCR, XCI, XCR, XCI, individual transformer, individual transformer leakage impedance at rectifier and inverter. Phi r, phi I, phi r within bracket phi I are the power factor angle at rectifier inverter. So, these are the different variables we have defined, and then what is left is for HVDC link. HVDC link, there is only one. There is only one there is ID is equal to VDR minus VDI by RDC, or RDC is the DC link resistance, and VDR, VDI is the DC voltage at the rectifier side, inverter side, these are understood. So, then what we have? So, we have got 5. So, for total in an HVDC link we have got 5 equations. So, now let us look, once we understand this, that these are the equations. So, now let us try to find out that what should be my unknown quantities. For the purpose of convenience, that how these are convenient we will show a little later in this discussion only, but for the purpose of convenience at each converter, at each side, the unknowns are chosen as as follows. At the rectifier, this is VDR, ID, AR, cos alpha and phi r. So, this is the unknown quantities, these are the at the rectifier. So, VDR, ID, AR, cos alpha, phi r. Similarly, at the inverter, VDI, ID, please note that ID would be the same because the HVDC link, the current at the rectifier and the inverter, they are same. So, AI cos gamma phi I. So, this is at inverter. So, then therefore, total unknowns are, so then total unknowns please note that these are chosen just for the sake of convenience. Now, how these are really convenient, that we will be looking into it when we will be trying to solve these 5 equations to solve for these unknowns. So, right now at this stage it is not apparent, but these are chosen just for the sake of convenience of calculation. So, the total unknowns combining these two are VDR, VDI, ID is common, then AR, then AI, then cos alpha, then cos gamma, then cos phi r, then phi r, phi I. So, these are the total unknowns. So, how many unknowns are there? Total 1, 2, 3, 4, 5, 6, 7, 8, 9. So, total 9 unknowns. So, total 9 unknown quantities. So, now what we have got? We have got total 9 unknown quantity. However, we have just now seen that for this HVDC link altogether we have got only 5 equations 1, 2, 3, 4 and 5. So, then therefore, I have got 9 unknowns and 5 equations. Obviously, we cannot solve for 9 unknowns by utilizing 5 equations. By utilizing 5 equations, we at best can only solve for 5 unknowns. So, then therefore, out of these 9 unknown quantities, 4 quantities need to be pre-specified and the rest 5 quantities actually need to be calculated. Now, the question is that which 4 quantities need to be specified. There is as such there is no hard and fast rule. Any 4 quantities can be pre-specified, and once these 4 quantities are pre-specified, then actually rest of the 5 quantities can easily be calculated by utilizing these 5 equations. Now, we may think that all these equations are actually nonlinear equations, because this involved cosine term, this also involved cosine term, this also involved cosine term, this also involved cosine term. Only the last equation does not involve any cosine term, but out of these 5 equations, 4 equations involve cosine term. So, then therefore, altogether these 5 equations seem to be basically non-linear in nature. So, we may think that after we pre-specify 4 quantities, then to solve these 5 remaining quantities we probably need to apply Newton-Raphson technique again to solve these 5 quantities, but this is not so. We can solve for these 5 quantities just by applying simple algebraic manipulation, and these algebraic manipulations are actually iteration free. That means, we can simply calculate the quantities of our interest analytically without going through any iterative process. Now, before we pre-specify the known quantities and the unknown quantities, again just for the sake of our recollection, let us just recollect for a while that what is the final objective of our calculation at the DC side in the case of sequential AC/DC load flow. So, what we discussed that in the case of sequential AC/DC load flow, what we do is that suppose we have one rectifier bus and one inverter bus. Please note that here at this bus there is a big grid and there is a big grid. So, there is a big grid and there is a big grid, and in this in between there is, for example, this transformer, then rectifier, and then here also transformer, then inverter. So, this is rectifier and this is inverter, and in between this rectifier and inverter there is a DC line. So, this is please note that there is some RDCs also there. So, this is the DC link resistance. So, this is VDR, this is VDI, and current is ID, and this is got 1:AR and this is got AI is to 1. Please note that this tap ratio is always at the side of this converter, and this is ETR, angle theta TR, this is ETI, angle theta TI. This rectifier has got an firing angle alpha, this inverter has got an extinction angle gamma, this rectifier has got number of 6 pulse converters is equal to NR, inverter has got number of 6 pulse converters is equal to NI. Usually these are 2, because here we are only talking about 12 pulse HVDC link. So, NR is equal to NI is equal to 2, and this has got XCR, XCI, etc. So, this is the arrangement. Now, what we are trying to do, basically what we are trying to do is that we do want to replace this entire circuit, we want to replace this entire circuit by some equivalent injection, and please note that some equivalent injection we call it PDR, we call it QDR, and here at this side also this is the, and here also we PDI, QDI. We are simply trying to replace everything from this to this, everything from this part to this part, everything from this part to this part by 4 equivalent real and reactive power injections. So, everything here. So, this net effect of this HVDC link would be reflected by this PDR, QDR, PDI, QDI at these 2 buses. This is again ETR, theta TR, and this is again ETI, theta TI. So, my objective is to replace this entire HVDC link by solving these 5 equations to arrive the values of PDR, QDR, PDI and QDI, such that after we get these equivalent power injections, After this we can simply treat them as far as this AC system is concerned. This entire DC link is gone, we have got only 4 equivalent power injections, and then after that standard AC load flow will continue. Now, so then therefore, our task is now to solve for these 5 unknown quantities, as we have just now said that although there are total 9 unknown quantities, but because we have got 5 equations. So, then therefore, you have to actually pre-specify 4 quantities, and after that the leftover 5 quantities need to be solved by utilizing this 5 equations, and after we solve these 5 quantities, then we will arrive at this PDR, QDR, PDI and QDI, and then subsequently we will solve the AC load flow. So, in the next lecture we will be looking at some cases that how to arrive at these values of PDR, QDR, PDI, QDI whenever we when we do specify 4 quantities, and then we do solve the rest of the 5 quantities utilizing these 5 equations. Thank you.